Okay, Assalamu alaikum students. We were studying chapter number 14, and this chapter number 14 is about the kinetics of particles by using the work energy principle. So we studied the conservation of energy principle in our last lecture. And now let's continue with the rest of the chapter. Okay, so let's start with the next topic, which is about power and efficiency. Okay, force is, work is basically what? Work is force into displacement into cos theta, between the force and the displacement. Okay, what is power? Power is work per unit time. Power is work per unit time. Yes.
Your voice is not clear.
My voice is not clear.
No.
I don't know. What is the problem with the voice? I don't know. Is it clear now? Is it clear now?
Yes.
Okay. So power is work per unit time. Okay. So it will be dW by dt. We can put W as force ds cos theta. Suppose if force and cos theta are constant, then they're going to go out and we have ds by dt. Okay, and so we have ds by dt is basically what? Ds by dt is velocity. So we have p is equals to force into velocity into cos theta. So force is a vector quantity. It has a specific direction. And velocity is also a vector quantity. It has a specific direction. So if the force and velocity are in the same direction, then theta will be 0 and cos theta will be 1. So this will be the formula for the power. Efficiency. Efficiency is output over input. So I just discussed this part. Is there anything within this part which is not clear to anybody? You can ask. Good. Okay. So let's. Okay, for the case of power, we have a unit of watt. It's joule per second, which is watt, and there are some other power units of power as well, which is horsepower. And horsepower can be converted into the SI unit and can be converted into English unit. So in the English unit, 1 horsepower is 550 foot-pound per second. In the SI unit, horsepower is 746 watt. Okay, so let's see the problem. The man in the figure pushes on the 50 kg crate with a force of 150 Newton. Determine the power supplied by the man when t is equals to 4 seconds. The velocity, the coefficient of kinetic friction between the floor and the crate is mu k 0.2. Initially, the crate is at rest. So the thing is that this man is pushing the crate, and obviously as he pushing the crate is will move in this direction, and there will be resistance force of friction between the crate and the floor, which will be acting in the opposite direction. The weight of the crate will be acting down, and there will be the normal force which will be acting up. So these are all the forces on the free body diagram, which is shown here. Okay, so what do we want? We want to find the power. Okay, so power is basically what? Power is F V cos theta, right? This is Fa cos theta. We want to find the power by the man when t is equals to 4 seconds. So when t is equals to 4 seconds, force is fixed, right? The force is not changing with time. So force, even and at 0 second, force is 150 Newton. At 4 second, the force will still be 150 Newton. So force is not changing. The angle is not changing, whatever the angle is being made between the force and the displacement. So that's not going to change. Velocity. We know the velocity when the crate is at rest. We don't know the velocity when the crate is at t equals to 4 seconds. Okay, so we know when t equals to 0 second, but we don't know when t equals to 4 seconds. So if we know the velocity, we can find the power. Okay, now for finding the velocity, since we know that the crate is moving, so there has to be some acceleration associated with it in the motion, and that means we can find the final velocity if we know the initial velocity and acceleration. So for finding the velocity, we can use this relationship. V equals to VI plus ACT. So when time is 4 seconds, initial velocity is 0. We can find what is the final velocity, but now we don't know the acceleration. So we can find the acceleration by taking the summation of forces in the x and the y direction. If we take the summation of forces in the y direction, there is a normal force acting up, then there is a component of the applied force acting down, then there is a weight acting down. So we get the normal force. When we take the summation F in x direction, we have the component of the force in the x direction, and we'll have the friction force, which will be 0.2 into n, but n we already know, so we'll find this thing equals to ma. This is the acceleration which we are going to substitute here, and then once we have this acceleration, we get the final velocity which we are going to substitute here, and so we'll get the power. How we know the angle? This is a good question. Look here, you know about this triangle, right? This is a pretty little triangle which normally they use in the book. 3, 4, 5. So can you find the angle using that? Okay, good. So this is how it's done. So actually the solution is done. If anybody want to ask anything in the solution of the problem, you can ask. Everything's clear so far? Good. So let's move ahead. Okay, let's have another problem. We have a 50 kg block A. So this is the block A, is 50 kg. So this is block A, 50 kg. Is hoisted by the pulley system and the motor. The motor has an efficiency 0.8. At this instant, the point P is this point, on the cable has a velocity of 12 meters per second, which is increasing at a rate of 6 meters per second. So at point P, we have the velocity and we have the acceleration, 12 meters per second and 6 meters per second square. Neglect the mass of the pulleys in the cable. Find the power supplied to the motor. Yes.
The example is not in the screen. We couldn't see it.
Really?
We see just example 1.
Is the screen frozen yet?
No, yes, we can see it now.
Does other students see the same problem, or I don't know?
No, it was shown.
Okay, so it's okay now? Okay.
Yes.
Okay, so we have once again we have 50 kg block A is hoisted by the pulley system and the motor. The motor has an efficiency of 0.8, At this instant, point P on the cable has a velocity 12 meter per second, which is increasing at a rate of 6 meter per second square. Neglect the mass of the pulleys in the cable. Find the power supplied to the motor at this instant.
Sir,
Yes.
still I can't see the question.
What is the problem? I don't know if the problem is on my side or your side. I don't know. Are other students facing the same problem that they cannot see
No,
the?
not the all.
No.
Maybe then it's because if it was a problem from my side, then all the students should have the same problem. Am I right?
Can I leave, then I sign again?
Sorry, I couldn't understand what you
Can I
said.
leave and sign again?
Yeah, sure. You can do this. You can leave and come back again. Okay. Shall we wait or shall I continue? I don't know. Good. Okay, can you see can you see the screen now correctly? Can you hear me?
I can see. Thank you.
Okay, good. Okay, so let's continue back. So we need to find the power supplied to the motor at this instant. So one thing you need to read here, look, it said that what is the power supplied to the motor? Look, this is the motor, okay? The motor is doing some work, okay? So the motor is pulling the rope with some power, but whatever the motor is doing, this is the output. Whatever the motor is doing, this is the output. Where does we supply power to the motor? We connect the motor to electricity. The motor runs with electricity. So we plug the motor and the electricity is the input power. We need to find what is the input power. What is the power supplied to the motor? Okay, so we have the formula for the efficiency because the motor efficiency is given. So efficiency of the motor is output, or I will say P out, put over power input. Okay, so we need to find power input. We know the efficiency. So if we know that what is the power output, we can find what is the power input. Okay, but power output is basically what? Power output is the actual work done by the motor. Actual work done by the motor means force into velocity. Okay, now I'm not going to put cos theta because the motor is pulling the rope in this direction and the rope is also moving in this direction. So the velocity and the force are both in the same direction. So theta is 0. So cos theta is 1. So I'm just going to write FV. This is the power. Okay, now F will be what? F will be the force with which the rope is being pulled by the motor. Okay, so that will be the tension inside the rope, right? So now if we know the tension in the rope, so instead of writing FV, let me write here TV. Okay, velocity of the rope at point P is given. So we know what's the velocity of the rope. Now, if we know the tension in the rope, we will find what is the output power. If we know the output power, we will find what is the input power. Okay, so, but we don't know the tension in the rope. Now, how can we find the tension in the rope? Because the rope is in motion, so what we can do is that we can make we can make a force balance at this point, at this pulley. This pulley is A. Okay, so if we make the force balance at this pulley, so we will have summation of there will be weight acting down and there will be two tensile forces acting up. This will be the same tensile force which is moving through because it's the same rope, so same tensile force. So that would be the same tensile force which we will have here. But the thing is that when we try to solve this, because when the rope is being pulled by the pulley, so this body A will be moving up. So we need to know what is the acceleration of body A. If we do the summation F is equals to MA, okay, we need to know what is A. So A is the acceleration of A, but we don't know acceleration of A, we know acceleration of point P. So now we need to find a relationship between point P and point A, or you can say here, point P and the acceleration of this pulley A. So now we have to do chapter number 12, last part, which was the dependent motion analysis. Okay, so if we do that, we will find what is the relationship between AP and AA. Okay, so we know AP, this is AP, acceleration at point P. If we know AP and we know the relationship between AP and AA, we will find AA. If we know AA, we will use it in this formula to find tension. If we know tension, then we know what is the power output. If we know power output, we know what is power input. Without going towards the solution of the problem, just speaking about the methodology that will be used to solve the problem, do you understand the methodology or not? Is the methodology clear? Okay, good. So let's see the solution. So first we needed to find what is the relationship between AP and AA. Now I don't need to go this with you. You went through this. Yes, it will be more clear when we will solve. Sure. So you see here, the first thing is that we need to find what is the relationship between point A and point P. Okay, so this is dependent motion analysis. We did it before in chapter number 12, by the end of chapter number 12. So we got this relationship. So based on that, since we know what is AP, acceleration at point P, we will find what is acceleration at point A. Now, once we know this thing, then we can apply the free body diagram. We can apply the force balance at pulley A, or at the body A. So weight is acting down, we have 2T up. So summation Fy equals to MA. So it will be negative 2T plus 490.5 equals to mass into acceleration. We'll find what is the tension. Once we know what is the tension, this tension is basically the force here. So we will get what is the power output. Once we know the power output, we'll get what is the power input. Okay, the problem is solved at this point, but I need to know if you really understood what happened here, or is there anything that you do not understand. You can ask.
Doctor?
Yes.
Why did we calculate the A? I mean, why we didn't take 9.8?
Why we didn't take 9.8? The thing is that this body A is moving up, okay, and it is moving. Its motion depends upon the power with which the rope is being pulled by the motor. So it's not a free body motion. It's not a free body motion, so we cannot take the acceleration as 9.8. For acceleration to be taken as 9.81, it has to be a free body motion. It's not being held by anything, or it should not be governed by any other motion. I don't know whether I understood your question properly or not. Did I understood your question properly, or am I answering something else?
No, right.
Okay. So if anybody has any question, please don't be shy. You can ask the question. I'll be happy to explain again. No problem. Okay, so I hope you understood. So let's move towards the next question. Okay, the motor of the hoist in figure 1416A lifts the 75-pound crate C so that the acceleration of point P is 4 feet per second square. So this is the motor. which is actually pulling the rope at point P. The acceleration is given 4 feet per second square. Determine the power that must be supplied to the motor. Again, we need the power that must be supplied to the motor. At an instant P has a velocity. Velocity is given at point P. Neglect the mass of the pulley in the cable and take efficiency as 0.85. It's actually the same problem. It's actually the same problem as we did last time. The only difference is that last problem was in the SI unit. This is in the English unit. Okay, so we need to have a relationship between AC and AP. Then once we have that, then we can use this in the summation of forces equation to find out the tension. Once we have the tension, we use this tension, multiply with the velocity to find out the power. Here they found the power in the horsepower, but it's not necessary because it's not asked in the question to put the power in horsepower. Okay, so they've calculated the power, converted it into horsepower, but this is the power output. Then put it into the formula for the efficiency to get the power input. Exactly the same problem as we did just last time. So anybody want to ask anything? Okay. Wait, what is this 32.2? Can anybody answer? Where is this coming from?
It's 9.81.
It's the acceleration, but
Yeah,
in weight.
yeah, but why do we need to use it here? Was there a G in the formula here? I don't see a G here. Summation F is equal.
Because we want MA, not the word.
We have the weight, so we divide by the acceleration.
Okay, good. I just wanted to see if the students are awake or not. It's okay. Okay, so this is done. Let's move towards the next topic. Next topic is conservation of energy. Okay, for starting the next topic, let's have a break of 5 minutes and then we'll start back, okay? Okay, students, let's start back. The next topic or the last topic for this chapter is about potential energy. Can you hear me properly?
Yes, we can.
Okay. Potential energy. You already know about potential energy. Most probably you studied about potential energy in physics. I don't know other courses, but maybe you have studied potential energy. So potential energy, we can analyze a system based upon the potential energy objects have while they are moving from one point to other point. Okay. So let's talk about potential energy. There are two kinds of potential energy I'm going to talk here. Okay. The first is the gravity potential. Now, gravity potential we represent here as Vg. Is basically what? It's the weight into the distance. Okay, weight into the distance, vertical distance that it travels. So this is gravity potential, or we can say gravity potential energy. But it has to be either plus or minus. Okay. Now, how do we determine if it's plus or minus? First, what we do is that we define a datum point. A datum point is our own selected reference point. Okay, so suppose this is our datum line. So this is our datum elevation. Okay, so if at any point, if our object is above the datum, then we say that corresponding to this datum, our object has some positive potential energy. So Vg is positive when it is above datum. Okay, when the object is below datum, we say that Vg is negative. Okay, because corresponding to our datum, it is below datum, so we say that it is negative. When the object is on the datum, then we say that Vg is 0. Okay, so this y is basically the distance, vertical distance from datum. Y is the vertical distance from datum. Okay, and how do we decide if Vg is positive or negative? Based upon if it is above the datum or below the datum or on the datum. Now you need to understand here one thing. It's an entirely different concept when we were considering about the work was positive or negative when something is moving up and down. Just try to focus here. When an object was moving up, what do you think? Work was positive or negative?
Negative.
It was negative. It was negative. When an object was moving up, work was negative. But here, when an object is above datum, gravity potential is positive. It's entirely opposite to it. It's a different concept. Don't mix it with the work. Okay, work of gravity is different than the potential energy here. Okay, it's a different concept. So don't mix the two things together. They both look like have the same formula, but they're different concepts. Okay, so we talk about the gravity potential. Gravity potential depends upon the datum. Okay, with reference to the datum, if an object is above the datum, we say that the object has potential, gravity potential inside it, and that is positive. And if the object is on the datum, we say that the gravity potential is 0. If the object is below the datum, we say the gravity potential is negative. When we were talking about the work of the gravity, which we discussed in chapter 14, part 1, the work of the gravity, if the object was moving up, that was negative. When the object was moving down, it was positive. That was the work of gravity. But here, we're talking about the gravity potential, not the work of gravity. Gravity potential. So gravity potential, it is in correspondence with our own selected datum. So if we have a datum selected, then if an object is above datum, that is positive potential. If an object is below datum, that is negative potential. If the object is on the datum, that's 0 potential. Before moving forward, I need to know, is this concept clear or not?
Doctor, here
Yes.
we talk about the position, not the movement, right?
Yes. Here we talk about the position, not the moment. Anything else anybody want to ask? Okay, let's move ahead. So this is one kind of potential energy, gravity potential. Now, let's talk about another kind of potential energy, which is the spring potential. Okay, so suppose if I have a spring, okay, suppose the spring is unstretched. I mean, the spring is in the original condition. No force has been applied onto it. Okay, so the S is 0. S is the stretch, right? So S is 0. So at this condition, we say that the potential of the spring is 0. The spring do not have any energy to do anything. It's in the original state. So spring potential is 0 when the spring is in the original state. Stretch is 0. Okay, but if there is a specific stretch, then we have a spring potential. So if you compress the spring or if you stretch the spring, now spring has some enough energy inside it that if you remove your hand or your power of stretching or compressing, the spring will do some work to return back to its original state. How the spring is doing the work? Because it has some energy stored into it. So it has some potential, okay? So the thing is that whether the spring stretches or compress, the potential is actually added into the spring. So suppose you had a spring in the original state. If I compress the spring, what I'm doing, I'm adding potential into the spring, because when I'm going to release my hand, automatically the spring is going to come back. How the spring is doing the work? Because I stored the energy as potential energy inside the spring while I was compressing it. On the same way, suppose I have a spring and now I start stretching it. So what will happen? As I'm stretching it, I'm adding energy as potential energy into the spring, because when I'm going to leave the spring, when I'm going to remove my hand, the spring is going to return back to its original condition. Now, while the spring is going back to its original position, the spring is doing some work. How does the spring is able to do some work? Because I added potential energy into the spring while I was stretching it. So in case of the spring potential, it can never be negative. The minimum is can be 0 when it is in the original state. But if you compress it, you are adding potential. If you stretch it, you are adding potential. Do you get the point here or not? Is it clear? Okay. So the formula for finding the spring potential is half Ks square, and there is no positive and negative here. It's always positive. So Vs cannot be negative. The minimum is that if there is no stretch, Vs will be 0. Okay. So we discussed about two things. We discussed about gravity potential. We discussed about spring potential. For the case of gravity potential, we need to make a selection of the datum point, and based upon the datum point, we're going to decide whether the potential is positive or negative. But for the spring potential, it can never be negative. Minimum is it can be 0 when the spring is in the original state, or either you compress it or stretch it, then it will be positive. And what will be the amount of the potential energy stored in it? It will be half Ks squared, where S is the stretch. Okay, so we talk about the potential. Okay, now let's talk about the conservation of potential or conservation of energy. So it's basically the kinetic and the potential energy initially equals to the kinetic and potential energy finally. Something you studied in physics and maybe other courses, where the energy, where we say that energy is conserved, it changes its shapes, or what do we say? It changes its forms from kinetic to potential or potential to kinetic, but overall remains conserved. So this is what it is. T1 plus V1 equals to T2 plus V2. But we say that V1 is of two kinds, VG1, VS1. Similarly, V2 is also of two kinds, VG2, VS2. So this becomes the complete formula. T1 plus VG1 plus VS1 equals to T2 plus VG2 plus VS2. So this is the conservation of potential or conservation of energy. Okay, so I can write it in terms of all the formulas. T1 is half mv1 is square, plus vg1 is plus minus wy1, plus vs1 is half ks1 square, is equals to T2 is equals to half mv2 square, plus vg2 is plus minus wy2, plus vs2 is plus half ks2 square. Do you understand this formula or not? Is there anything which is not clear in this formula? Please ask. Okay. No clear. What does it mean? Not clear? If anybody wants to ask anything, instead of writing, you can directly open the mic and ask. That's easier. Okay. Okay, so I need this screen. Put it here. Okay. Okay, so let's move towards. Okay, example 4. The 2 kg collar is moving down with a velocity of 4 meter per second at A. So at A, we have, at this point A, we have the velocity of the collar 4 meter per second. This collar itself is 2 kg. Okay, with the velocity of A. The spring constant is 30 Newton per meter. The unstretched length of the spring is 1 meter. So unstretched length is 1 meter. The velocity of the collar, we need to find the velocity of the collar when S is equals to 1 meter. Where is S? S is this. Okay, this is 1 meter. Okay, so now let's try to see that what do we have one by one. Okay, we have 2 kg collar, so mass is known, mass is given. Okay, mass is given. Okay, then just yeah, so we have 2 kg collar, so okay, so the mass is given. We know what is the mass. Okay, the next thing is that initial velocity at A, the velocity of the collar is 4 meter per second. So we know the velocity, V1. Okay, and what do we want? We want to find the velocity of the collar when S is equals to 1 meter. So we need to know what is V2. Okay, so this V2 is unknown. This is what we want to find out. Okay. Okay, so the collar is moving down. Now we need to select a potential. So we can put point A as the datum. We need to select a datum. We can put point A as the datum, or we can put point C as the datum. So what do you want? Do you want point A to be put as a datum or point C?
Point A.
Okay, so let's put A as the datum. So this is our datum now. Okay. So this is our datum now. So if our datum is here at A, so what do you think Y1 will be? Y1 will be 0, yes, because Y1 is actually at our datum. Okay, so Y1 will be 0, so this whole term goes to 0. Okay, K value is given, so we know the K. Okay, S1, what would be S1? S1 would be the unstretched length of the spring is 1 meter, and initially when it is at A, the total length of the spring is 2 meter. So what do you think? What is S1?
Zero.
No. Unstretched length is 1 meter, but at A, the total length of the spring is 2 meter. So 2 minus 1 equals to 1. You get it or not?
No, it's not clear.
Look, at A, what is the total length of the spring? Can you see here? 2 meter. It's okay. And unstretched length of the spring is 1 meter. If suppose the spring was not stretched, then the length of the spring is 1 meter. So at A, how much is the stretch? Out of 2 meter, 1 meter is the unstretched length, so remaining is the stretch. Did you get it? I think not. Look, at A, the spring is already stretched. How much it is stretched? Because it is said that the
Okay, so it's a 2 meter after the stretch.
Yeah, at A, it is already stretched. How much it is stretched? Because the total length is 2 meter. So 1 meter was the unstretched length. So remaining is actually the stretch. Did you get it now?
Yes.
Okay. So we know S1. Okay. Okay, so what do you think point C? Point C is below our datum, right? So positive or negative? Negative, yes. Because it is below our datum, so it has to be negative. Okay, weight is known. We know the mass, so we can put what is the weight. Okay, and Y, how much below datum is S? This is given that when S is equals to 1 meter. So we know Y2 as well. Okay, now what will be stretch 2? What will be S2 here when the collar is at C? Now how can we find that?
S minus 2.
No. Unstretched length
Pythagoras.
is
Yes, we use Pythagoras.
yes, we need to use Pythagoras theorem. So we know that this is S is equals to 1 meter. This length is 2 meters. So we have the perpendicular, we have the base. We can find what is the hypotenuse. Hypotenuse is going to give us the total length. Total length minus unstretched length is going to give us S2. Okay, so if I say this is hypotenuse, then S2 is basically what? S2 is hypotenuse minus unstretched length, which is 1. Unstretched length is 1. Okay, and this hypotenuse is this. Now, how do you find hypotenuse? This is a right angle triangle. So you know S, you know this, you know perpendicular, you know base, you can find hypotenuse. So only one thing unknown, which is V2. So can we find V2? Before moving over to the solution of the problem, I need to ask, do you understand the solution of the problem? Is there anything which is not clear? Please ask.
The doctor,
Yes.
when S is equal to 1 meter, does this mean when A reach C, reach point C?
You see here, this is one of the things I discussed before as well. You need to be very clear. Yes, when S is equals to 1 meter, that means that it has reached point C. But remember, this S is a distance here, and this S is not the same as S1 or S2. Okay, because the book uses the same variable for the distance, same variable for the stretch. Okay, so you get confused. Okay, it says that the velocity of the collar when S is equals to 1 meter. This S is mentioned here. This is just a distance. Okay, and here in the formula we have ks1 square, ks2 square. This S are the stretches, not the distance. Okay, this is a good question. Will it be clear in the exam? S for what? I don't know, but you should see the problem and get to know which S you are talking about. Okay, so it would be the same way because we are following the same book and maybe the same numericals from the book. So it will be the same way as I'm teaching here right now. If you want me to use different symbol, maybe I can use different symbol. Let's say for the distance, I can use D. That is better.
Yes.
But in any case, you should understand the concept. Okay, so before moving over to the solution of the problem, is it clear so far, everything? Yes. You are saying it is very confusing that S in the gives is given different than S in the diagram. Yeah, it's true. It's confusing. And there you'll find this confusion throughout this book. I mean, I told you from the beginning, we cannot do anything. This confusion is there within the book. We are solving, we are following this book, not just from now, from statics. We have been following Hibbeler, and the Hibbeler has done this thing. So you have to live with it and understand what they have done it. It's confusing, true. It's confusing, but so you have to live with this confusion. Okay. Let's move ahead. So you see here, first, okay, they also took the datum at A. Okay, so we can find the potential at C, and in the same way, then kinetic energy, then potential at A, kinetic energy at A, then summation of everything. So that's it. When they're taking potential at C, that it's a combination of gravity potential and spring potential. Sometimes it's written as E. E means elastic potential. Elastic potential is the same as the spring potential, because we say that the spring is elastic. Okay, so actually the problem solution is done here. Before moving over to the next problem, I need to know, anybody wants to ask anything, you can ask. Okay, and let's move ahead. Okay, the 800 kg roller coaster starts from A with a speed of 3 meters per second. So this is a roller coaster, and it is 800 kg, and it starts from A with a speed of 3 meters per second. So at this point, we know the speed, 3 meters per second. Find the minimum height of the hill so that the car travels around inside loop at B without leaving the track. Also find the normal reaction on the car when the car is at C for this height of A. Okay, again, within the statement, there is a code here. It's coded. Okay, and the code is that find the minimum height of the hill so that the car travels around inside loop at B without leaving the track. Okay, so when it leaves the track, what happened is that, look, the car is always in contact with the track, and the roller coaster moves like this, then takes a loop. When it comes to B, okay, there is a possibility that it can leave the track. If it leaves the track, now it is no more in contact with the track. So when it is no more in contact with the track, that means the normal reaction would be 0, because normal reaction comes when you have contact with the track. So we want to find out the minimum height such that it moves through the loop B without leaving the track. Since we want to know the minimum height, that means we need to find the point when it actually leaves the track. What should be the height when it actually leaves the track? So that means that would be the minimum height. You can keep the height higher than that, not less than that. So we solve it for the limiting case. Okay, and then once we have solved for the limiting case, now we know that, okay, what is the limit? So that's the idea here, that we have to solve it for the case when the normal reaction at B will be 0. Now, how do we know that the normal reaction at B will be 0? These two statements are basically the code for that. Now, decoding the code here is difficult if the solution is not in front of you, and this is true, but this is true throughout the book. So anyways, let's see the solution. Okay, so we have the car. First, what we can do is that we can solve between point A and point B. Okay, let's say here in the book they've taken point A as the datum. Okay, so if you're solving between point A and point B, the roller coaster as it moves throughout the track. So when the roller coaster moves on the track, there will be, okay, the potential, gravity potential will be there, but there's no spring here. Spring potential is not there. So let me cut this out. So it's just the gravity potential and the kinetic energy. At point A, we know what is the, at point A, we know what is the kinetic energy because we know what is the velocity. We know what is the mass. We know what is the mass. Okay, so we need to find that what is the velocity at point B. This is, we don't know. Okay, now at A, since we took our datum at A, so gravity potential at A will be 0. For B, since B is below our datum, so it will be negative, and we know the weight. Okay, and we know that this, what is this y2? Okay, this y2 is the h. This is what we need to find. This y2 is the h. This is what we need to find. So the thing is that now we know, now we have in this equation two unknowns. What is h? So it will be h minus 20. It will be h minus 20 because the radius here is 10. So that's this distance. Okay. This will be y2. Okay, so now we have one equation with two unknowns, where VB is unknown and H is unknown. Okay, now how can we find VB? We can apply the equilibrium of forces in the normal direction at point B. So summation Fn equals to MAN. Okay, where AN will be the velocity at B square upon rho. Rho is the radius of curvature. Radius of curvature is 10 known. M is known. Okay, and the summation of forces. What kind of forces do we have at B? If we are talking about the limiting case, so for the limiting case is the case when actually the roller coaster leaves the track, and when the roller coaster leaves the track, then at that point the normal force of the track on the roller coaster will be 0, and it will be just the weight of the track which will be the force acting. It will be just the weight of the roller coaster which will be acting. So for that limiting case, NB will be 0 approximately, and it will be just the force or the of weight. So we just put here Fn is the weight. So we get what would be the VB for this case. We substitute that VB here, we'll get the height. This is the limiting height. If we put this height, then if we put this height of point A, then the roller coaster will actually fall down. So our height should be more than this. In any case, this is the limiting case. Before moving forward, do you understand the concept of the problem so far? Is there anything which is not clear? The problem statement is not easy. I mean, if I'm the student myself, it won't be easy for me to have an understanding that at B, the normal force is 0. This is what written in the question. Okay. Why h minus 20? This y2 is basically what? Y2 is the distance of point B from the datum. Our datum is the top. Okay. So distance of point B from the datum is this distance. But how much is this distance? Because this is complete h, and the radius here is 10 for the loop at B. So the diameter will be 20. So complete h minus 20 will be h minus 20. Is it clear? Okay. Anybody else who want to ask anything? Okay, so what was asked next? Next, it was asked, also find the normal reaction of the car when the car is at C for this height of A. So it's like solving the problem again for C, for point C, okay, and find the normal reaction at this point. So we can solve it between point A and C again. This time, first we solved between point A and B. Now we're going to be solving it between point A and C. So when we solve it between point A and C, now we know the height. So we will directly find what is the velocity at C. And once we have the velocity at C, we can find out what is the normal reaction at C. So the problem solution is simple actually, but if anybody wants to ask anything, you can ask. Is the solution of the problem clear or not? Okay. Okay, let's have this one last more problem, and then after that we will consider that this chapter is done. Okay. Okay, the gantry structure in the photo is used to test the response of an airplane during a crash. As shown in the figure, the plane having a mass of 8,000 kilogram or 8 megagram is hoisted back until theta is 60 degree, and then the pullback cable AC is released when the plane is at rest. Determine the speed of the plane just before it crashes into the ground when theta is 15 degree. Also, what is the maximum tension developed in this supporting cable during the motion? Neglect the size of the airplane and the effect of the lift caused by the wings during the motion. So the question is that we have this structure, and this structure is designed to test the airplane crash. So the initial position of the airplane when the airplane was at rest is when theta is 60 degree, and the airplane is going to crash when theta is 15 degree. Okay, so we need to find the speed of the plane just before it crashes. What will be the speed of the plane when it crashes? So initial velocity is 0. First of all, there is no spring here, so just cancel these terms. Initial velocity is 0, so initial kinetic energy is also 0. Okay, final velocity, okay, mass is known, velocity we need to find out. What is the final velocity? Okay, and let's talk about the potential, gravity potential. It's already mentioned in the diagram where is the datum. So if this is the datum, then point A is below the datum and point B is also below the datum. So both are below the datum, so this will also be negative and this will also be negative. Both will be negative. Weight is known, we know the weight. Y1 and Y2 we can find because the rope is like 20 meter, and when the theta is 60 degree, so it will be 20 cos 60. And when the theta is 15 degree, then it will be 20 cos 15. So that's how we'll determine what is Y1, what is Y2, and that's it. You solve the problem, you get what is V2. Is the solution procedure clear or not? Okay. Anybody wants to ask anything? Okay, you can see here we're doing between point A and point B, and that's it. We find the velocity, and after that we need to find out that what is the tension in the cable. So we can do it by using the summation of forces in the normal direction. MAN, so we now know the velocity, so and divide by the radius of curvature, which is 20, which is actually the length of the string. And the forces which are acting at this point, it will be just the weight of the, it will be just the weight of the, it will be a tensile force in the string minus the component of the weight in the direction of the string. So it will be 8,000 into 9.81 cos 15. So we'll find out what is the tension in the string. So now you can see this is the normal direction. The tension in the spring in the normal direction, but the weight is acting down. It's making an angle 15 degree here at the point of crash. So the component of the weight in the normal direction will be opposite to the tension. So that's how it's done. So actually the solution of this problem is also done. So if anybody want to ask anything, you can ask. Otherwise, in reality, our chapter number 14 is finished now. And next week, inshallah, we are going to start chapter number 15.
Doctor,
Yes.
it's clear, but can you repeat only how can we find the distance, the y?
Why? Okay. Okay, distance y. So when we're talking about the distance y, so you see here, this is our datum. Distance y will be the vertical distance of point A. Now, if this is 20 meter and this angle is 60 degree, So it will be 20 cos 60. This will be y1. Is it clear?
Yes.
Okay. And when this plane has reached to this point, then this will be 15 degree, and the distance from the datum will be this distance. Okay, this distance, and so it will be what? This is a total cos 15. It's clear?
Yeah, clear. Thank you.
Okay. Okay, one student is asking, Doctor, when I solve example 2, chapter 14, part 1, I couldn't determine S1 and S2 for the spring. Could you please resolve it, just how to find them? Chapter 14, part 1, you're asking. Okay, so let me open chapter 14, part 1. You're saying example 2. This one, right? You couldn't determine what is S1 and S2. Okay, so am I right? Did I understand correct? What do you want to ask? Okay, good. So let's do it again so that you can understand. Look, when S is equals to 0.6, the spring is not stretched or compressed. So the original position or original thing is that S is zero point 0.6. When this distance is 0 0.6, then this spring is in the original state, not stretched nor compressed. Okay. And the 10 kg block, which is subjected to a force of 100 Newton, has a speed of 500 down this road. Find the distance when the block stops. So we need to find the distance when the block stops. Okay, so here we need to use the formula for the spring. Okay, so it will be work of the spring is basically, we're going to talk about is plus minus half k S2 square minus S1 square. Okay, so initially what we are saying, first of all, it is from the plus minus, we are going to say that since the spring is stretched, so it would be negative, because the work and the because the force and the displacement are in the opposite direction. Okay, so it will be negative. K is known. Okay, so now we have to talk about S2 and S1. So since we say that in the initial condition, when S is 0.6, this is not stretched, this is not compressed. Okay, so S1 is actually 0. So what will be S2? So then we can find out what is S2. So S2 is basically, because we don't know the distance, okay? We don't know the distance. So S2, we can just keep it as what? S2. Okay, we can just keep it as S2. And when we are going to solve it, we're going to find S2. Okay, now this S2, from S2, we can determine what is S, because the relationship is that S2 is equals to, or you can say S is equals to S2 plus 0.6. Okay, or S2 is equals to S minus 0.6. This is a relationship, because initially S1 was unstretched position and it was 0. So this, at that point, S is equals to 0.6. So when it is fully stretched, that is S2. So S2 will be whatever the stretch we have plus 0.6. I don't know whether I'm able to give you the understanding or not. So you have to understand, this length is S. Okay, this is 0.6. When this is 0.6, S1 is 0. Okay, so when this is stretched to, let's say, uh, let's say it comes to this point, and here S2, whatever the S2 we have here, then S will be from here, from our reference point. So it will be S2 plus 0.6. So that will be the total S. So total S will be S2 plus 0.6. Here S2 we are saying as a stretch. Now here in the solution, when they say S2, so S2 they mean the total length. That's the difference. Okay. So here when they're saying it S2 is the total length. So you have to just first figure it out that what you are referring to it as S and what you are referring to as S. So the best way is that if you solve the same problem, but instead of saying this as S, let's call this as D, distance, so that nobody get confused. Let's say this is D. Okay. So if I say this is D, so when D is 0.6, S1 is 0. What will be the D when S1 when we will find S2? Okay, so the relationship will be what? The total distance, or let's say call this is D1, let's call this D2. So total distance D2 will be S2 plus 0.6. Is now thing a little more clear or not? Okay. So I don't know whether you understood or not, but it's a little hard thing to explain when you need to have an imagination to think what's happening here.
Doctor,
Yes.
I have a question in the same lecture. Example.
In this lecture, part 1.
Yes.
Okay.
Example 4.
Example.
Example 4.
Example 4. Okay. You want me to solve this problem?
No, I want to ask about the work of spring. Why it's positive?
Work of the spring, why is positive? Let me just look at it. What's the problem? What the question is? The platform shown has negligible mass and is tied down so that 0.4 meter length cord keep a 1 meter long spring compressed when nothing is on the platform. If 2 kg block is placed on the platform and released from rest after the platform is pushed down 0.1 meter, determine the maximum height this block rises in the air measured from the ground. Now you have to understand one thing, that the initial condition is that the spring is stretched and you have spring is compressed and you have put the block. That's the initial condition. Okay. Now when you remove the block, so what's happening? The spring was already compressed. Now it is decompressing. You remember I discussed about 4 states: stretch, de-stretching, compressed, decompressing. Okay, so when it is de-stretching or decompressing, then the work of the spring is positive. Do you get it?
Yes, but the problem is when I calculate S1 and S2, this I think this so the summation is minus, so it's confusing.
Okay. Once again, because we are making my way of solution is a little different. What I do is that I make a decision myself initially whether it's going to be positive or negative. Once I have already made the decision whether the work will be positive or negative, okay, now when I say S2 and S1, okay, so I just put bigger value minus a smaller value. You get it? So that I get a positive answer there, because I have already made the decision whether the work done by the spring will be positive or negative.
So just I put the sign according to if
Yes,
it's
put the sign,
compressed or
put the sign according to the nature of the problem, and then when you are putting the value of S1 and S2, just put higher value minus a smaller value.
okay.
You get it?
Yes. Also, I have a question in example 6.
Example 6. Okay. Okay.
The work of A here.
The work of A. Okay.
Why it is positive?
Why? What is positive?
Yeah, the work of A. The
A.
gravitational work of this object A.
Okay. So what's the question actually? Block A and B shown in the figure have a mass of 10 kg and 100 kg respectively. Determine the distance B traveled when it is released from rest to the point where its speed becomes 2 meters per second. Okay. So why the work of A is positive here? It's not positive. You can put it negative.
But I get different velocity.
Okay, you have to understand one thing. When you're putting the work of the A, okay, here we have to see, because A is, if B is moving down, A has to be moving up. When the A is moving up, that means work is negative, right? When the A is moving up, then the work is negative. So, but you are making a relationship between B and A as well at the same time. Okay, so the relationship of B and A is such that they are opposite to each other. Okay, so corresponding to that, when you are doing the summation of forces, did we do the summation of forces here? No, we just did this. So I don't know, I have not solved the problem here with you right now, but I think if you put A negative, the work of the A negative, then it should give you the right answer. I don't know why you're saying that it's giving you the wrong answer. So what they have done here, work of A, where is the work of A? A delta S A. Okay, so delta S A is equals to -4 delta S B. So SB, okay, they put SB as, they put SB as positive. VB they're putting as positive. Since they're putting VB as positive going down, that's why VA is coming negative. So you have to put VB as negative then, because it is going down. It has to be consistent with your conventions of the work going up and down. So I don't know. Try it, and all the other students also try it. If you feel difficulty, then we will discuss this problem later.
Okay. Thank you.
Okay. Anybody else want to ask anything? Okay, if nothing, then that's it for today.
Doctor,
Yes.
what's the material that are included in the exam?
What is the material that are included in the exam? I need to talk with Dr. Salim first in this regard. So, look, I think we are moving fast. I think Dr. Salim group is moving a little bit slow, because even one of their class, they missed it during that holiday for the for the Independence Day here. So I need to ask that what material they have covered, and then based on that we are going to decide that. Because right now we are done with chapter number 14, and this is the 6th week, and your exam is in the 8th week, right? So 7th week we are going to do first part of chapter 15. So at least till chapter number 14 we can give for the exam. So 12, 13, 14 we can give for the first exam. But I need to see that part has been covered by Dr. Salim group. And then based on that, we'll decide. So if 14, not 12, 13 is for sure. But 14, we're going to decide when I'm going to talk with Dr. Salim.
Okay, thank you.
Okay. Okay, that's it for today.